The solid ground of reality dissolves at the atomic horizon. Our everyday intuition fails completely where classical physics ceases to make sense, and particles can be in two places at once. The physicist Niels Bohr once said that anyone who is not shocked by quantum theory has not understood it. By the end of this exploration, you will grasp the profound mysteries that make our universe so beautifully strange. We will uncover how a cat can be both alive and dead, and why particles billions of miles apart can communicate instantly. What does it truly mean for certainty to be an illusion? Physics seemed almost complete at the dawn of the 20th century. Many scientists believed the major work was done, that the universe operated like a magnificent, predictable clockwork machine. All that remained was to tidy up a few minor details. But those details refused to be tidied. They were tiny cracks in the foundation of classical physics, and they would soon shatter our entire understanding of reality. One of the most stubborn problems was a phenomenon known as blackbody radiation. Imagine a perfectly dark object that absorbs all light and then, when heated, glows. Classical theory predicted that such an object would emit an infinite amount of energy at very high frequencies, a result so absurd it was called the ultraviolet catastrophe. It was a clear sign that the established laws were breaking down. Into this crisis stepped Max Planck. In a desperate move to make the math work, he proposed something radical. He suggested that energy is not released in a smooth, continuous flow, like water from a hose, but in tiny, indivisible packets. He called these packets quanta. Planck himself was hesitant about this idea, seeing it as a mere mathematical trick. But then a young Albert Einstein took it seriously. He applied the concept to light itself, proposing that light travels not just as a wave, but as a stream of particles, which we now call photons. This explained the photoelectric effect, where light shining on metal kicks out electrons, but only if the light's color, not its brightness, is just right. This was the birth of quantum theory. The paradigm had shifted irrevocably. The smooth, predictable universe of Newton was giving way to a grainy, digital one where energy came in chunks. Planck introduced a fundamental constant of nature, a tiny number now bearing his name, that sets the size of these energy packets. How would it feel to see the very rules you built your career on suddenly rewritten? What does it mean for our reality if the fabric of the cosmos is not a continuous sheet, but is woven from discrete, tiny threads? This was not a minor adjustment. It was the first step into a much stranger world, a world where the solid ground of classical physics would soon dissolve beneath our feet. The universe was supposed to be a perfect, predictable machine. Yet this new quantum reality revealed a fundamental flaw in that grand clockwork. The first and perhaps most unsettling limit we encounter is the complete breakdown of determinism. Where classical physics promised certainty, quantum mechanics offers only probability. This shift began with a young physicist named Werner Heisenberg. He discovered that at the subatomic level, there is a fundamental limit to what we can know. His uncertainty principle states a simple yet profound truth. It is impossible to know both the exact position and the exact momentum of a particle at the same time. The more precisely you pin down one, the more the other becomes a blur. Think of trying to measure the exact location of a single, fast-moving firefly in a pitch-black room. To see it, you need light, but the moment a single photon of light bounces off the firefly to reveal its position, you have disturbed its path, changing its momentum. At the quantum scale, the act of observation itself changes the reality you are trying to measure. Heisenberg himself described this not as a limitation of our instruments, but as a fundamental property of nature. This principle shatters the classical dream of Laplace's demon, the idea that a vast intellect knowing the position and motion of every atom could calculate the entire future of the universe. The demon cannot even know the present with perfect accuracy. The future is not written in stone. It is written in a haze of probabilities. This is where the mathematics takes us into even stranger territory. Erwin Schrödinger's famous equation does not describe solid particles moving along definite paths. Instead, it describes a wave function, a cloud of possibility that tells us where a particle is likely to be found. This probability density is the particle's true state before we look at it. An electron does not orbit a nucleus like a planet around a star. It exists as a shimmering cloud of potential locations, being everywhere it possibly can be at once, until the moment we measure it. This is the state known as superposition. Consider the unsettling example of radioactive decay. Take a single, unstable atom. We can calculate its half-life, the time it takes for there to be a 50% chance it has decayed. But we can never predict the exact second that this specific atom will fall apart. The event is fundamentally random, governed by chance, not by a hidden clockwork we simply cannot see. This inherent uncertainty forces us to ask deep questions. If the universe is not a predetermined chain of cause and effect, does that open a door for genuine free will? How do we navigate a world where the most fundamental layer of reality refuses to offer guarantees? Embracing this probabilistic nature is our first step into the truly bizarre. A world where objects can exist in multiple states simultaneously, waiting for a look to make up their mind. This probabilistic blur forces us to confront an even deeper strangeness. What is the true nature of the things that make up our world? Are they tiny, solid balls or spread out, ethereal waves? The answer, bafflingly, is that they are both. And which one they choose to be depends entirely on how we ask the question. This is the enigma of wave-particle duality. Light, which we once thought was purely a wave, can also act like a stream of particles, as Einstein showed with the photoelectric effect. But then a French prince, Louis de Broglie, turned this idea on its head. He proposed that if a wave can act like a particle, then every particle should also act like a wave. He suggested that all matter, from electrons to baseballs, has an associated wave nature. This seemed like pure speculation until experiments proved him right. When electrons are fired at a crystal, they do not simply bounce off like tiny marbles. They create a diffraction pattern, a series of rings that can only be explained if the electrons are behaving as waves, interfering with themselves. The most stunning demonstration of this duality is the legendary Double-Slit Experiment. Imagine a barrier with two narrow, parallel slits cut into it. Behind it is a screen that lights up whenever a particle hits it. Now, if you fire a stream of tiny particles like bullets at the barrier, you would expect to see two distinct bands on the screen behind the slits, a pattern of hits directly in line with each opening. This is exactly what happens with classical particles. But when you perform this experiment with electrons, something miraculous occurs. Even when you fire them one at a time, with long pauses in between, they do not build up two bands. Instead, they slowly paint a series of light and dark stripes, an interference pattern. This is the unmistakable signature of a wave. A single electron, it seems, passes through both slits at once, like a wave spreading out, and then interferes with itself on the other side to create the pattern. The moment you place a detector to see which slit the electron actually goes through, the magic vanishes. The electron stops behaving like a wave. It picks a single slit, like a good particle, and the beautiful interference pattern disappears, leaving just two boring bands. The very act of looking, of trying to pin down a definite path, forces the electron to abandon its wave-like nature. The physicist Richard Feynman saw this as the central mystery of quantum mechanics. A phenomenon, he said, contains all of its deep magic. How can a single object be in two places at once, acting as a spread-out wave of possibility, only to collapse into a single, localized point the instant we observe it? This leads us directly to the heart of the quantum world. a state where things are not just one thing or the other, but exist in a blurred combination of all possibilities at once. This blurring of a single object's identity leads to an even more profound limit on our classical reality. A particle is not forced to choose a single state. It can, and does, inhabit multiple contradictory states at the exact same time. This is the principle of quantum superposition, a direct assault on our everyday either-or logic. The most famous and deliberately unsettling illustration of this is Erwin Schrödinger's thought experiment involving a cat. He proposed a scenario where a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers a mechanism that shatters the vial, killing the cat. Since the radioactive decay is a quantum event, the atom exists in a superposition of both decayed and not decayed states. According to the bizarre rules of the quantum world, the entire system inside the box, including the cat, becomes linked to this state. Therefore, until someone opens the box and looks, the cat must be considered both alive and dead simultaneously. Schrödinger did not actually believe a cat could be both alive and dead. He created this paradox to highlight what he saw as the absurdity of applying quantum weirdness to the large-scale world we live in. He was pointing out a glaring problem. Where does the quantum world of multiple possibilities end, and the classical world of single, definite facts begin? The mathematics, however, handles this superposition with elegant precision. The state of a quantum system is described by a state vector, a kind of arrow in an abstract realm called a Hilbert space. This arrow points to a combination of all possible states the system can be in. An electron orbiting an atom is not just in one energy level. It exists in a superposition of all its allowed levels, a fuzzy cloud of potential, until a measurement forces it to pick one. This is not just theoretical. It is the fundamental engine of the coming quantum computing revolution. A classical computer bit can only be a 0 or a 1. A quantum bit or qubit can be a 0, a 1, or any complex combination of both 0 and 1 at the same time. This is like a light switch that is not just on or off, but is in a state of being both on and off to varying degrees. This allows a quantum computer to explore a vast number of possibilities simultaneously, solving certain problems that would take classical computers thousands of years in a matter of minutes. Think of a single atom that has been excited by a pulse of light. It does not instantly fall back to its ground state. For a period of time, it exists in a shimmering superposition of both its excited and ground states, a tangible reality of being two things at once. If the fundamental particles that build our world do not have definite states until observed, what does that say about existence itself? Does an electron truly exist in a specific place, or is it more accurate to say it is a set of relationships, a web of potentialities? This blurring of identity at the root of all matter challenges our deepest notions of what it means to be an object. And when these superposed particles interact, they can forge a connection so intimate and instantaneous that it defies our understanding of space and time, a phenomenon that links their fates across the universe. This blurring of identity becomes even more profound when two particles become deeply intertwined. Their separate realities dissolve into a single, shared existence. Two particles can be born from a single quantum event, forever linked in a dance of perfect correlation. This is the phenomenon of quantum entanglement. No matter how far apart they travel, their fates remain locked together. Measure the property of one, and you instantly know the property of the other. Albert Einstein was deeply troubled by this idea. He saw it as a violation of the cosmic speed limit set by his own theory of relativity, the rule that nothing can travel faster than light. He called it spooky action at a distance, a phrase that perfectly captures its unsettling nature. Along with his colleagues Boris Podolsky and Nathan Rosen, He crafted a powerful thought experiment now known as the EPR paradox. They argued that if quantum mechanics was correct, it would allow for this spooky instantaneous influence which seemed absurd. Therefore, they concluded, quantum theory must be incomplete. There must be some hidden variables, some deeper, unseen properties that predetermine the particle's states all along, restoring a sensible, local reality. For decades, this remained a philosophical debate. Then, a brilliant physicist named John Bell found a way to test it. He devised a mathematical theorem, now called Bell's theorem, which laid out a clear experimental path. If hidden variables existed, the correlations between entangled particles would fall within a certain limit. But if quantum mechanics was correct and the world was truly spooky, the correlations would be stronger. In the 1980s, a French physicist named Alain Aspect performed a series of meticulous experiments. He created pairs of entangled photons and measured their properties in different directions. The results were unequivocal. The correlations violated Bell's limit. The universe had chosen spookiness. There were no hidden variables. The connection was real and instantaneous. Imagine a pair of magical dice. You take one die to Paris and the other to Tokyo. You roll the die in Paris and it shows a 3. At that exact instant, you know the die in Tokyo also shows a 3. But it is not just that you know it. The act of your measurement in Paris seems to force the die in Tokyo to take on that specific value. This is not just a prediction. It is how we create ultra-secure quantum cryptography. If anyone tries to eavesdrop on an entangled message, their act of measurement disturbs the delicate quantum link, immediately alerting the sender and receiver to the intrusion. This strange connection is forged in laboratories every day. Scientists use a crystal to split a single photon into 2 lower-energy, entangled photons. These photon pairs fly off in opposite directions, perhaps for miles through optical fibers. Their polarizations, the direction in which their light waves oscillate, remain perfectly linked. If one is measured to be vertically polarized, its twin will instantly be horizontally polarized, no matter the distance between them. This forces us to confront a startling possibility. Does this mean we are sending information faster than light? The answer, surprisingly, is no. You cannot use entanglement to send a message like a quantum text. While the correlation is instantaneous, the outcome of your measurement is completely random. You cannot control whether you get a vertical or horizontal photon. The person with the other photon also gets a random result. It is only when you later compare your notes over a classical, slower-than-light channel that you see the perfect, spooky match. The universe seems to be fundamentally interconnected in a way that bypasses space and time. 2 particles can act as a single entity, even when separated by the width of a galaxy. This non-locality suggests that the separateness of objects may be an illusion, a temporary appearance in a deeper, unified whole. If the state of one particle can be decided by a measurement made light years away, what does that say about the role of the one who is looking? The observer is no longer a passive witness, but seems to be an active participant in shaping reality itself. This intimate connection between entangled particles forces a profound question. What is the role of the one who is looking? The moment we reach out to measure this quantum world, it seems to shrink from our touch, its shimmering possibilities solidifying into a single, definite fact. This is the 5th and perhaps most mind-bending limit, the observer effect, where the simple act of looking changes what is seen. Think of a soap bubble floating in the air, shimmering with a rainbow of colors. It exists in a delicate, fragile state of many possibilities. The moment you reach out to touch it, to confirm its reality, it pops. The quantum world behaves in a similarly elusive way. A particle exists in a spread-out cloud of potential, a superposition of many states, described by its wave function. But the instant a measurement is made, that wave function collapses. All the other possibilities vanish, and the particle snaps into a single, concrete location or property. It is as if the particle was waiting for a question before it decided on its answer. Early interpretations, like the Copenhagen interpretation championed by Niels Bohr, took this at face value. They proposed that the particle truly has no definite properties until it is measured. The act of observation is what brings reality into being. This led to some startling speculations. The brilliant mathematician John von Neumann suggested that the collapse of the wave function might be tied to consciousness itself. He described a chain of measurement. A particle interacts with a measuring device, which interacts with the scientist's retina, which interacts with their brain. According to the pure math, the entire chain, from particle to brain, should become entangled in a giant superposition. Yet we never experience a superposition of thoughts. We only see one outcome. Von Neumann argued that it must be the immaterial consciousness of the observer that finally causes the collapse, cutting the chain and defining a single reality. This idea was pushed even further by Eugene Wigner with his friend thought experiment. Wigner imagined his friend in a lab performing the Schrödinger's cat experiment. From Wigner's perspective outside the lab, until he opens the door and asks his friend what happened, the entire lab, including his friend and the cat, should be in a superposition. Is the friend both having seen a live cat and having seen a dead cat until Wigner consciously learns the result? This seems absurd, highlighting the deep puzzle of where to draw the line. But is the observer effect just a physical disturbance, like Heisenberg's famous microscope where light photons bump into electrons? For true wave function collapse, the answer is no. The strangeness goes deeper than mere bumping. A more modern understanding points to a process called decoherence. A quantum system is incredibly delicate, maintaining its superposition through a coherent, in-step relationship between its possible states. But the moment it interacts with its messy, unpredictable environment, with even a single stray air molecule or a photon of background heat radiation, this coherence is destroyed. The superposition leaks away into the environment, and the system behaves classically. The measurement apparatus and the environment are effectively performing constant, unconscious observations, forcing quantum systems to choose a state long before a human is ever involved. This explains why we do not see cats that are both alive and dead. A cat is far too large and complex to avoid constant decoherence from trillions of interactions with its environment. The power of the observer is dramatically illustrated by the quantum Zeno effect. Named after an ancient Greek philosopher, this effect shows that a watched pot never boils, at least in the quantum world. If you have an unstable particle that is likely to decay, but you repeatedly and rapidly measure it to see if it has decayed, you can actually freeze it in its original state. The constant observations, like a series of rapid-fire questions, reset the particle's internal quantum clock, preventing it from evolving and changing. It is a stunning demonstration that measurement is not a passive act, but an active intervention that shapes the system's destiny. So, does reality require a conscious mind to exist? The answer remains one of the greatest mysteries in science, a puzzle known as the measurement problem. We have precise mathematical laws that describe how a wave function evolves smoothly in a superposition. And we have a rule that says measurement causes an abrupt, random collapse. But we have no fundamental theory that explains why or how this collapse happens, or what truly qualifies as a measurement. This blurring of the line between the observer and the observed suggests that we are not separate from the universe looking in, but deeply integrated participants in the unfolding of reality itself. This boundary between the quantum and the classical is the source of the deepest unanswered question in physics: what exactly constitutes a measurement? The equations of quantum mechanics describe two very different processes. There is the smooth, predictable evolution of the wave function, where possibilities spread out and overlap. And then there is the abrupt, random collapse into a single outcome the moment a measurement occurs. The problem is that the theory itself does not define what a measurement is or when it happens. It simply postulates two rules without a clear line between them. This is the measurement problem, the final and most profound limit on our classical reality. The traditional Copenhagen interpretation, championed by Niels Bohr, sidesteps the issue by declaring measurement as a fundamental, irreducible process. In this view, the quantum world is a realm of potential, and the classical world of detectors and observers is a separate, objective stage. The act of measurement is what translates possibility into actuality. There is no deeper explanation, it just is, but this left many physicists deeply unsatisfied. If measurement is a physical interaction, why is it special? This line of thinking led to the radical proposal by Hugh Everett, known as the many worlds interpretation. Everett took the mathematics at face value. He suggested that wave function collapse is an illusion. There is no collapse at all. Instead, at the moment of a quantum decision, like the decay of a radioactive atom, the entire universe splits. In one branch, the atom decays and the cat dies. In another, perfectly real branch, the atom does not decay and the cat lives. Every possible outcome of every quantum event actually occurs, spawning an endless, branching multiverse of parallel realities. As physicist David Deutsch put it, the multiverse is not a theory in itself, but the explanation for why quantum theory works. In this view, we are unaware of our other selves because our conscious experience splits along with the universe, following a single thread in an infinite tapestry of possibilities. This eliminates the need for a special measurement rule, but at the cost of an almost unimaginable cosmic extravagance. Other theories seek a more concrete dividing line. Roger Penrose, for instance, proposes that gravity is the key. He suggests that when a quantum system becomes massive enough for its own gravitational field to be significant, the inherent instability of spacetime causes the wave function to collapse spontaneously. For Penrose, the fuzzy quantum world and the definite classical world are separated by a gravitational horizon. This is an objective collapse theory, where the transition is driven by physics, not by observation. So when does the fate of Schrödinger's cat get decided? Is it when the atom interacts with the Geiger counter? When the hammer strikes the poison vial? When the cat's nervous system registers the event? Or only when a human mind becomes aware of the result? The von Neumann-Wigner interpretation places the ultimate collapse at the step of consciousness, an idea that gives the observer a truly cosmic role, but feels uncomfortably mystical to most scientists. The most practical modern answer comes from decoherence. This explains why we do not see superposition in the everyday world. A system as large and complex as a cat is constantly bombarded by its environment. Trillions of air molecules, photons of light, and vibrations continuously interact with it, effectively measuring it billions of times a second. This relentless interaction destroys quantum coherence, making the system appear classical. Decoherence explains the appearance of collapse, but it does not solve the fundamental measurement problem. It tells us why superpositions are so fragile, but it does not explain why, out of all the possibilities, we experience only one specific outcome. The universe seems to operate with two sets of rules, one for the tiny and one for the large, with no clear signpost marking the transition. Is reality fundamentally uncertain until a conscious mind observes it? Or do all possible realities exist in a vast, unseen ensemble? Or is there a physical trigger we have yet to discover? The measurement problem remains a gaping hole in our understanding, a silent question mark at the heart of physical reality. This transition from quantum possibility to classical fact is not a sharp line, but a blurry horizon. The universe seems to operate by two different sets of rules, and the mystery of where one ends and the other begins is one of the most active frontiers in physics. The key to understanding this boundary lies in a process called decoherence. Think of a quantum system, like an electron in a superposition, as a perfectly still pond. When you drop two stones into the pond, they create sets of ripples that spread out and interfere with each other, creating a complex, beautiful pattern of peaks and troughs. This is quantum coherence, the state of being in multiple possibilities at once, perfectly in step. But what happens if a strong wind suddenly blows across the pond's surface? The delicate interference pattern is quickly destroyed, churned into a chaotic mess. The wind represents the environment, and this is decoherence in action. The moment a quantum system interacts with the outside world, whether it is a single photon of light, a molecule of air, or even the faint warmth of its surroundings, that perfect coherence is lost. The system's multiple possible states become out of sync with each other, and they can no longer interfere. The superposition effectively vanishes, and the system begins to behave like a classical object with a single, definite state. Physicist Wojciech was a pioneer in showing how this relentless environmental interaction explains the emergence of the classical world from the quantum one. Decoherence answers the question of why a dust particle floating in a sunbeam is never seen in two places at once. That dust particle is constantly being bombarded by billions of air molecules. Each collision is like a tiny, unconscious measurement, forcing the particle to localize. The timescale for this process is incredibly fast for large objects. For a dust mote, decoherence happens in a tiny fraction of a second, far quicker than any human could hope to observe. The larger and more complex a system becomes, the more connections it has to its environment, and the faster it loses its quantum nature. Experiments are now pushing this boundary, creating quantum states with larger and larger objects. Scientists have successfully put molecules composed of thousands of atoms into a state of superposition, sending them through double-slit experiments where they interfere with themselves. These are not single electrons, but vast, complex structures behaving as waves. They are carefully isolated in ultra-high vacuum chambers and chilled to near absolute zero to minimize environmental contact, creating a tiny pocket of quantum reality in our classical world. This leads to a profound question. Is the quantum classical boundary an objective physical divide, or is it merely subjective, dependent on how much we can isolate a system from its surroundings? If we could perfectly isolate a cat from every stray photon and air molecule, would it, in theory, be able to exist in a superposition of alive and dead? The answer from decoherence theory suggests that for any object that large, perfect isolation is practically impossible. The internal interactions within the cat itself, the trillions of chemical processes and atomic collisions, would cause it to decohere instantly. We are not separate from this process. Our own bodies and brains are vast, warm, wet systems, constantly undergoing decoherence, which may be why our thoughts feel like single, definite streams and not a blur of all possible thoughts at once. Yet, the very fact that we can engineer quantum states in increasingly large systems hints at a deeper truth. There is no fundamental law that says large things cannot be quantum. It is just exponentially harder to maintain that delicate state of coherence. This ongoing struggle to protect quantum systems from their environment is the central challenge in building quantum computers. Understanding this boundary does more than just solve a philosophical puzzle. It is the essential bridge that leads us to our most accurate description of reality, a framework where the quantum and the classical are seamlessly woven together, a theory that governs everything from the smallest particles to the largest stars. This blurry horizon between the quantum and the classical is not the final frontier. To truly grasp the nature of reality, we must take one more profound step, moving beyond the idea of isolated particles to a vision of the universe as a vibrant, dynamic tapestry of energy. We step into the realm of quantum field theory, a framework where the very concept of a particle is transformed. Here, an electron is not a tiny, solitary ball. Instead, it is a localized excitation, a tiny knot of vibration in a universal, all-pervading electron field. A photon is a ripple in the electromagnetic field. Every fundamental entity is an inseparable part of its own underlying field, a cosmic ocean that fills all of space. This synthesis, born from the marriage of quantum mechanics and Einstein's special relativity, began with Paul Dirac. His equation for the electron was a work of mathematical genius, not only describing the electron's properties, but also miraculously predicting the existence of its antimatter counterpart, the positron. It was a stunning validation that this new path was correct. The development of quantum field theory required a new way of calculating, a new language for particle interactions. This is where Richard Feynman's diagrams come in. These deceptively simple pictures of lines and vertices are not just drawings. They are a powerful mathematical shorthand, each diagram representing a precise calculation for how particles scatter and transform. A straight line is an electron propagating through space-time. A wavy line is a photon. A junction where they meet is an interaction. The true magic is that these interactions are mediated by virtual particles. These are not particles you can ever directly catch or measure. They are fleeting borrowings of energy from the vacuum, allowed by the uncertainty principle, that pop into and out of existence just long enough to transmit a force. Think of the electromagnetic force between two electrons. In this picture, the two electrons repel each other not by magic, but by constantly tossing these virtual photons back and forth, like two people in canoes throwing a rapid volley of baseballs between them, pushing each other apart. Quantum field theory's predictive power is breathtaking. It perfectly explained a tiny, puzzling shift in the energy levels of the hydrogen atom, known as the Lamb shift. This minuscule difference, undetectable by older theories, arises from the electron constantly interacting with the quantum fluctuations of the electromagnetic field around it. The electron is subtly jostled by this sea of virtual particles, changing its energy ever so slightly. Physicist Freeman Dyson spoke of the profound elegance of this framework, a theory of infinite degrees of freedom that nonetheless yields exquisitely precise answers. This entire edifice culminates in the standard model of particle physics, a triumph of human intellect built on the foundation of quantum field theory. It is a tapestry woven from matter fields for particles like quarks and electrons, and force fields mediated by particles like photons and gluons, all governed by mathematical principles known as gauge theories. This framework tells us that the vacuum of empty space is not empty at all. It is a seething, bubbling cauldron of potential, alive with transient fluctuations. How does this change our view of a particle? It means that what we call an electron is not an object, but an event. It is a localized vibration in an eternal, universal field. Its solidity is an illusion of its persistent excitation. And if the vacuum is not empty, but full of this latent activity, what does that say about the nature of nothingness itself? This vibrant, fluctuating void holds the keys to the next great mystery, a hidden energy woven into the fabric of spacetime itself. This seething quantum vacuum is anything but empty. The void itself is alive with a faint, eternal crackle of energy. The same uncertainty principle that blurred a particle's position and momentum also applies to energy and time. It allows for a remarkable loophole in the law of energy conservation. For an incredibly brief moment, a particle and its antiparticle can spontaneously pop into existence from nothing, borrowing energy from the vacuum before annihilating each other and vanishing back into the void. These are virtual particles, ghostly apparitions that flicker in and out of existence everywhere all the time. Hendrik Casimir, a Dutch physicist, found a way to prove this bizarre activity was real. He predicted that if you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, they would be gently pushed together. This is the Casimir Effect. The reason is a stunning consequence of vacuum fluctuations. In the empty space outside the plates, virtual particles of all wavelengths can pop into existence. But in the narrow gap between the plates, only particles with wavelengths that fit perfectly can form. With more activity outside than inside, the virtual particles themselves create a subtle pressure, pushing the plates together. It is as if you stood in a quiet room with windows open to a bustling street. The sound waves from the street would push against you from the outside, but the quiet inside would offer no counter-pressure. This faint pressure has been measured in laboratories, a direct whisper from the quantum vacuum. This background hum of creation and destruction is known as zero-point energy, the lowest possible energy that a quantum system can have, which is not zero. It is the reason an atom never completely freezes to absolute zero. Its electrons are constantly jostled by this sea of virtual particles. This zero-point energy is not just a curious effect. It drives one of the most fundamental processes in the universe, spontaneous emission. An atom excited by a pulse of light should, classically, remain excited forever. But it does not. It eventually falls back to its ground state, emitting a photon. What pushes it? It is the vacuum itself. The fluctuating electromagnetic field nudges the atom, triggering its decay. The vacuum is not a passive stage but an active participant. This energetic vacuum even holds the key to one of the most dramatic phenomena in astrophysics, Hawking radiation. Stephen Hawking realized that near the immense gravity of a black hole, virtual particle pairs can be torn apart. One particle falls into the black hole while the other escapes into space. To a distant observer, this stream of escaping particles looks like radiation slowly leaking from the black hole, causing it to evaporate over astronomical timescales. The black hole is literally powered by the energy of empty space. Yet this vibrant vacuum also presents physics with its most embarrassing problem. When physicists calculate the total zero-point energy of all these fluctuations, the answer is absurdly, catastrophically large. It should be enough to curve the entire universe into a tiny, dense ball. This is the cosmological constant problem. The fact that our universe is expanding at the rate it is, and is not a tiny knot, means that the observed energy of the vacuum is 120 orders of magnitude smaller than the calculated value. It is the worst mismatch between theory and observation in all of science. So is empty space truly empty? The quantum vacuum is a roiling ocean of potential, a dynamic medium that shapes the behavior of every particle. It triggers atomic decay, pushes metal plates, and may one day cause black holes to fade away. How can nothing be so full of activity? This constant churn of the vacuum does more than just create particles. It allows for a strange kind of magic, a phenomenon where particles simply vanish from one side of a wall and reappear on the other. This shimmering quantum vacuum, alive with fleeting particles, suggests that nothing is truly forbidden. A particle can face a barrier that should be completely impenetrable. A wall it simply does not have the energy to climb, and yet it can suddenly appear on the other side. This is quantum tunneling, the ultimate escape act. It is as if you threw a ball at a hill, and instead of rolling back, it vanished from your side and instantly reappeared on the far slope, having passed straight through the mountain. In the rigid world of classical physics, this is pure magic. But in the quantum realm, it is a daily occurrence. The explanation lies in the wave-like nature of particles. Remember the wave function, that cloud of probability describing where a particle is likely to be found. When this wave encounters a barrier, it does not abruptly end at the wall. Instead, it decays exponentially, fading away like a whisper. But if the barrier is thin enough, the wave function does not drop entirely to zero before the other side. There remains a faint, non-zero probability that the particle will be found there. It has effectively tunneled through. The probability of this happening depends on the particle's mass, the barrier's height, and most critically, its width. A thinner barrier makes tunneling far more likely. This is not just a theoretical curiosity. It is the very reason our sun shines. Deep in the sun's core, protons need to collide and fuse to create helium and release energy. But they are all positively charged, and they fiercely repel each other. The energy required to overcome this repulsion and get them close enough to fuse is far greater than the energy the protons actually possess from the core's immense heat. Classically, nuclear fusion in the sun would be impossible. But thanks to quantum tunneling, there is a small but real chance that a proton will tunnel through this electrostatic barrier. This happens constantly in vast numbers, powering our star and making life on Earth possible. George Gamow, along with Ronald Gurney and Edward Kundin, was one of the first to use this quantum phenomenon to explain a great mystery, the radioactive decay of atomic nuclei. In alpha decay, a cluster of 2 protons and 2 neutrons escapes from a nucleus. The nuclear force holding it in is like a deep well, surrounded by a tall barrier created by electrostatic repulsion. The alpha particle should be trapped, but its wave function leaks through the barrier, giving it a small probability of appearing outside the nucleus every second. This tunneling probability directly determines the half-life of the radioactive element, which can range from tiny fractions of a second to billions of years. How does tunneling challenge our notion of impossibility? It reveals that barriers are not absolute walls, but are instead more like probabilistic filters. There is always a chance, however small, that the forbidden will happen. This principle has been harnessed by our own technology. The Scanning Tunneling Microscope, or STM, is a revolutionary invention that lets us see and manipulate individual atoms. It works by bringing an incredibly sharp metal tip very close to a surface. A small voltage is applied, and electrons tunnel through the empty space between the tip and the surface. The current of these tunneling electrons is exquisitely sensitive to the distance. By scanning the tip across the surface and keeping the current constant, the instrument traces the atomic contours, producing stunning images of the atomic landscape. This device, which relies entirely on quantum tunneling, opened the nanoscale world to our eyes. The same principle is at work in many electronic devices, like flash memory and tunnel diodes, where electrons tunnel through insulating layers to create switches and memory states. This non-classical motion feels almost like teleportation, a ghostly passage through solid matter. If the fundamental particles that build our world can perform such feats, what other impossibilities are merely probabilities waiting to be realized? This ghostly passage through solid barriers reveals a deeper truth about information itself. In the quantum world, the most precious property a particle possesses is its unique quantum state. But how could you possibly transmit that state to another location without ever sending the particle itself? The answer is quantum teleportation, a protocol that sounds like science fiction but is grounded in laboratory fact. It allows the exact state of one particle to be recreated in a distant particle, effectively teleporting its quantum identity. The process was first proposed in a landmark paper by Charles Bennett and his colleagues in 1993. Bennett described it not as a form of travel, but as a way of making one object become the same as another, using what he called disembodied transport of information. The entire procedure rests on the spooky foundation of quantum entanglement. Here is how it works. First, you need a pair of entangled particles. Let us call them particle B and particle C. You give particle B to your friend who takes it to a distant location. You keep particle C. Now you have a third particle, particle A, whose unknown quantum state you wish to teleport. Your goal is to make particle B, far away, become an exact replica of particle A. You begin by performing a special joint measurement on your two particles, A and C. This is known as a Bell state measurement, and it entangles these two particles together. This act has a remarkable consequence. It instantly transfers the quantum information from particle A to the distant particle B, by way of the entanglement link you already established. But there is a crucial catch. The information is scrambled. It is like you have instantly mailed a locked box to your friend, but the key to the lock is a random piece of classical data generated by your measurement. To complete the teleportation, you must send this key to your friend using a normal, slower-than-light communication channel, like a radio signal or a phone call. Only with this classical information can your friend perform the final step, applying a specific operation to particle B, to unscramble it and reconstruct the exact original state of particle A. During this entire process, the original particle loses its unique state, a necessary result of the no-cloning theorem. This fundamental rule of quantum mechanics states that it is impossible to create an identical copy of an unknown quantum state. Teleportation cleverly sidesteps this by destroying the original in the process of creating the perfect replica elsewhere. The physicist Anton Zeilinger and his team were pioneers in demonstrating this experimentally, first teleporting the polarization state of a photon across a lab bench. His work showed that teleportation is not limited by distance, only by our ability to maintain the fragile entanglement link. They later extended these experiments over many kilometers, using optical fibers and even between the ground and a satellite. This leads to a natural question. Since the entanglement link seems to act instantly, does this violate Einstein's theory of relativity? The answer, once again, is no. The actual transmission of useful information requires the final classical signal. Without that random key, the person with particle B has no way of knowing what state it is in or how to decode it. The instantaneous entanglement correlation is useless for sending a message faster than light on its own. This makes quantum teleportation a perfect protocol for future quantum networks. It is the essential mechanism for moving quantum information between different nodes in a quantum internet, all while the underlying quantum cryptography ensures the process is completely secure from eavesdroppers. So, what are the ultimate limits? We cannot teleport a person or even a single atom with today's technology. The process becomes exponentially more difficult as the system grows larger and more complex. But we can teleport the state of a single photon, and that alone opens a universe of possibilities. If the identity of a particle can be recreated across space, what does that say about the nature of the particle itself? Is it the physical stuff that matters, or is it the information it carries? This promise of perfectly secure communication is not a distant dream. It is being built today, using the very laws of physics to create locks that are fundamentally unbreakable. This is quantum cryptography, a field where an eavesdropper cannot even listen without giving themselves away. The most widespread method is called quantum key distribution. It does not send the secret message itself through quantum means. Instead, it uses quantum particles, typically photons, to distribute a random secret key. This key is then used with classical encryption to scramble the actual message. The magic lies in how that key is shared. The foundational protocol, known as BB84 after its creators Charles Bennett and Gilles Brassard, relies on the quirky behavior of photon polarization. Imagine that the polarization, the direction a light wave oscillates, is the language of the key. The sender, traditionally named Alice, prepares each photon in one of two possible bases or sets of directions. She might use a rectilinear basis, meaning the photon is polarized either vertically or horizontally. Or she might use a diagonal basis, meaning it is polarized at 45 degrees or 135 degrees. For each bit of the key, she randomly chooses a basis and sends a photon polarized in one of its two states. The receiver, Bob, does not know which basis Alice used for each photon. He must guess. For every incoming photon, he randomly selects a rectilinear or diagonal filter to measure it. If he guesses the correct basis, he will measure the polarization correctly. But if he guesses wrong, the result is completely random. He has a 50% chance of getting the wrong bit value. After the transmission, Alice and Bob talk openly over a classical channel. They discuss only the bases they used for each photon, not the actual bit values. They discard all the bits where Bob used the wrong basis. The remaining bits where their bases matched form their preliminary secret key. Now, how do they catch an eavesdropper? Let us call the eavesdropper Eve. If Eve tries to intercept the photon stream to learn the key, she faces the core quantum rule. She cannot measure a quantum state without disturbing it. Just like Bob, she has to guess which basis to use for each photon. Half the time, she will guess wrong. When she does, her measurement forces the photon into a new, definite state, and she sends this now altered photon onto Bob. Later, when Alice and Bob compare a small subset of their key bits over the public channel, they will find errors in places where their bases matched. The presence of these errors reveals Eve's intrusion. They simply discard the compromised key and start over. As physicist Arthur Eckert later showed, this security can also be built on the even stranger foundation of quantum entanglement. In his E91 protocol, Alice and Bob each receive one photon from an entangled pair. Because their properties are perfectly correlated, they can generate a shared secret key simply by measuring their particles. Any attempt by Eve to measure one of these photons breaks their delicate entanglement, introducing detectable errors just as before. This is spooky action put to work. To make these systems practical over long distances, researchers have developed clever techniques like decoy states, which help defeat certain hacking attempts by sending photons with different intensities. And since photons are absorbed over long fiber optic cables, quantum repeaters are being developed. These are like miniature, secure relay stations that can extend the range of quantum keys across continents. The real world is already taking notice. Major banks and government agencies are testing quantum key distribution to protect their most sensitive financial transactions and data links. It creates a vault where the very act of looking inside triggers an alarm. How does this redefine security? Classical encryption relies on mathematical problems that are merely hard to solve with current computers. A powerful enough machine could crack them. But quantum cryptography's security is based on immutable physical laws. It does not matter how much computing power an adversary has. They cannot bypass the uncertainty principle. This shift from computational security to physical security could one day make our digital world as secure as the laws of nature allow. What does a society look like when its most vital communications are sealed with quantum locks? This technology, born from fundamental research, is now driving the development of the hardware that will power the next leap. The quantum computers that could both break old codes and create new, unbreakable ones. These unbreakable quantum locks rest on a foundation of profound strangeness, a foundation that is now being harnessed to build an entirely new kind of computer. This machine does not think in simple zeros and ones. It dances in the realm of superposition and entanglement, solving certain problems with a speed that is not just faster, but exponentially, almost magically, faster. This is the promise of quantum computing. The fundamental unit of this new computer is the qubit. Unlike a classical bit, which is definitively a 0 or a 1, a qubit can be both at the same time. It exists in a superposition of states, a combination of 0 and 1, described by a wave function. This single property unlocks a phenomenon called quantum parallelism. With just 300 qubits in superposition, a quantum computer could represent more states simultaneously than there are atoms in the known universe. It can explore a vast landscape of solutions all at once. David Deutsch, a visionary physicist, laid the theoretical groundwork by defining a quantum Turing machine. He saw that such a device could not just simulate our universe, but could compute in a way that classical machines fundamentally cannot. The power is not in raw speed, but in a different kind of logic. To manipulate qubits, we use quantum gates. These are not physical gates, but precisely controlled operations that rotate the qubit's state, changing its probability landscape. A sequence of these gates forms a quantum algorithm, a choreographed dance that amplifies the correct answer and cancels out the wrong ones. One of the most stunning algorithms came from Peter Shor. He showed how a quantum computer could factor enormously large numbers into their prime components with breathtaking efficiency. Why does this matter? Because our modern digital security, the RSA encryption that protects everything from online banking to state secrets, relies entirely on the fact that this factoring problem is impossibly hard for classical computers. Shor's algorithm, if run on a sufficiently powerful quantum machine, would break that security, rendering current encryption obsolete. This is not a distant threat. It is a mathematical certainty that drives much of the research in post-quantum cryptography today. But quantum computers are not just code breakers. Another brilliant algorithm, Love-Grover's search algorithm, can find a single, unique item in an unsorted database with a quadratic speedup. Imagine searching a phone book with 1,000,000 names for a single number. A classical computer might need to check all 1,000,000 entries in the worst case. Grover's quantum algorithm could find it after only about 1,000 checks. This has profound implications for searching massive datasets, from drug discovery to complex logistics. Building these machines, however, is a monumental engineering challenge. The qubit itself is a fragile thing. It can be a single electron, its spin representing the 0 and 1. It can be a trapped ion, held perfectly still by electric fields and manipulated with lasers. Or it can be a tiny loop of superconducting wire, where current flows both clockwise and counterclockwise at the same time. But all these qubits face the same enemy, decoherence. The slightest vibration, a stray photon, or even the warmth of the surrounding environment can cause the qubit to collapse from its delicate superposition into a definite, classical state. This is the quantum classical boundary, the same blurry horizon we encountered before, now playing out inside a cryogenically cooled chip. To fight decoherence, physicists are developing sophisticated error correction codes. The idea is to spread the information of one logical qubit across many physical qubits. By constantly measuring these helper qubits for signs of error, without collapsing the main qubit's state, the system can detect and correct mistakes faster than they accumulate. This creates a kind of fortress around the quantum information, protecting it from the noisy classical world. So what problems can only quantum computers solve? They excel at simulating quantum systems themselves, a task that is exponentially difficult for classical machines. Modeling a complex molecule for a new drug, or understanding high-temperature superconductivity, could become trivial for a fault-tolerant quantum computer. They will not replace our laptops for browsing the web or writing documents, but they will open doors to discoveries in materials science, chemistry, and artificial intelligence that we can barely conceive of today. How will they change technology? They will force us to rebuild the foundations of our digital security, and they will give us a computational lens to see deeper into the fabric of nature itself. The race is on to build a machine that can fully tame the quantum world, not just as a subject of study, but as the most powerful tool humanity has ever wielded. But that delicate quantum state is incredibly fragile. Like a perfectly clear bell ringing in a silent room, its pure tone can only last so long before the air itself begins to dampen the sound. This gradual fading from a quantum chorus into classical noise is known as decoherence, the relentless enemy of quantum coherence. It is the process that explains why we do not see quantum weirdness in our everyday world, and why building a quantum computer is one of the hardest technological challenges we have ever faced. Decoherence occurs when a quantum system, like a qubit in superposition, interacts with its surrounding environment. This could be a single molecule of air, a stray photon of light, or even the faint warmth of the materials holding the qubit. Each interaction is like a tiny, unconscious measurement, forcing the quantum system to leak information into the outside world. The system's multiple possible states, once perfectly in step, become jumbled and out of phase with each other. They can no longer interfere, and the beautiful, useful superposition collapses into a single, definite, classical state. Physicist Wojciech profoundly advanced our understanding with his concept of environment-induced superselection, or einselection. He showed that the environment does not just randomly destroy quantum states. It acts as a predictability sieve, selectively favoring states that are robust against these interactions. These stable states are the ones we recognize as classical. They are the pointer states, like the definite position of a dust particle, that do not get rapidly scrambled by the environment. The mathematics behind this uses a tool called the density matrix, which describes the statistical state of a quantum system. For a pure, isolated qubit in superposition, the density matrix shows clear off-diagonal terms. These are the quantum correlations, the signature of coherence. As decoherence sets in, these off-diagonal terms fade to zero, washed out by environmental noise. The matrix becomes diagonal, representing a simple mix of classical probabilities. The timescale for this, the decoherence time, is brutally short for large objects. For a dust mote, it happens in a fraction of a microsecond. For a complex molecule, it might be milliseconds. For a single electron carefully isolated, it could be much longer. The larger and more complex the system, the more connections it has to its environment, and the faster its quantum nature evaporates. Consider a superconducting qubit in a quantum computer. It is a tiny circuit chilled to a fraction of a degree above absolute zero, where electricity can flow both clockwise and counterclockwise at once. But even there, decoherence lurks. A single high-energy photon from the outside world, or a subtle vibration from the refrigerator, can strike the qubit. This interaction forces it to choose a direction, collapsing the superposition and ruining the calculation. The race to build a practical quantum computer is largely a race against decoherence. How can we protect these fragile quantum states? The primary method is extreme isolation. We build elaborate shields, use ultra-high vacuums, and cool systems to near absolute zero to minimize environmental contact. But perfect isolation is impossible. So we also rely on quantum error correction. This is a brilliant scheme where we encode the information of one logical qubit into a complex state of several physical qubits. By carefully measuring these helper qubits, we can detect the telltale signs of decoherence and correct errors without ever directly looking at it, and thus collapsing the main qubit state. Is decoherence a fundamental limit of physics, or just a practical engineering barrier? Most evidence suggests it is the latter. There is no law of nature that says large things cannot be quantum. It is just exponentially difficult to prevent them from talking to their surroundings. This understanding even helps us explore the frontiers of quantum biology, where phenomena like photosynthesis in plants and navigation in birds may rely on maintaining quantum coherence in warm, wet, and seemingly chaotic environments. If life has found ways to subtly harness quantum effects despite decoherence, what other secrets might be hiding in plain sight? The fragile dance of quantum coherence is not confined to frigid laboratories. It thrives in the most unexpected of places, within the warm, wet, and seemingly chaotic systems of life itself. This is the frontier of quantum biology, a field that asks how living organisms might harness quantum mechanics to survive and thrive. For decades, it was assumed that quantum effects would be instantly wiped out by decoherence in biological environments. Life was considered too hot, too messy, to host such delicate phenomena. But nature, it seems, has found a way. One of the most compelling examples is photosynthesis, the process by which plants convert sunlight into chemical energy. When a photon of light strikes a leaf, it excites an electron in a chlorophyll molecule. This energy needs to travel to a reaction center to be stored. Classically, we might picture this energy hopping randomly through the forest of molecules, a slow and inefficient process. But experiments reveal something far more elegant. Using ultrafast spectroscopy, scientists like Graham Fleming have observed that the energy does not take a single path. Instead, it explores multiple routes simultaneously, a clear signature of quantum coherence. It is as if the energy is a wave spreading through the molecular antenna, sampling all possible pathways at once to find the most efficient route to its destination. This quantum-assisted search allows the transfer to be nearly 100% efficient, a feat our best solar cells cannot match. The plant is not just using chemistry. It is using quantum physics to outmaneuver decoherence, maintaining coherence long enough to perform a vital biological function. This quantum ingenuity extends to our very sense of smell. Theorist Luca Turin proposed a radical explanation for olfaction, suggesting our noses might detect not just a molecule's shape, but its quantum vibrations. The theory posits that odorant molecules in the nose undergo electron tunneling, where an electron tunnels across a receptor, but only if the molecule's vibrational frequency matches. This would allow us to distinguish between molecules that are chemically identical but vibrate differently, a mystery that shape-based theories struggle to explain. Perhaps the most stunning quantum sense belongs to migratory birds. The European robin travels thousands of miles, guided by the faint whispers of Earth's magnetic field. The prevailing theory suggests this magnetic compass relies on entangled radical pairs. In a protein in the bird's eye, light creates a pair of molecules, each with an unpaired electron. These two electrons become quantum entangled, their spins linked. Earth's magnetic field, incredibly weak at this scale, influences the quantum spin states of this entangled pair. Depending on the field's orientation, the pair's chemical fate changes, creating a signal that the bird's brain can interpret as a direction. This is not a vague hypothesis. Experiments show that disrupting certain light wavelengths or introducing magnetic noise can confuse the birds, while artificial magnetic fields can manipulate their orientation. They are not just following a line. They are perceiving the world through a quantum lens, feeling the subtle tug of the planet on the correlated spins of entangled electrons. Even the enzymes that catalyze the chemical reactions of life appear to use quantum tunneling. These biological machines often need to transfer a proton or an electron to make a reaction proceed. The energy barrier for this transfer can be high, but tunneling allows the particle to simply appear on the other side, speeding up reactions by factors of millions or more. Life seems to have evolved to exploit this quantum shortcut, making essential processes possible at the gentle temperatures of a living cell. These discoveries force us to reconsider the very fabric of life. How widespread are these quantum effects? Could even consciousness, that most elusive of phenomena, have a quantum component? Some theories, like the Orch or model proposed by Roger Penrose and Stuart Hameroff, suggest that quantum computations in the microtubules of brain cells might play a role. though this remains highly speculative and controversial. The true revelation of quantum biology is not that life is quantum, but that it has mastered the art of protecting coherence. It builds molecular pockets that shield quantum states just long enough for them to be useful, turning decoherence from an enemy into a managed resource. If a simple plant or a bird can harness spooky action and tunneling, what does that say about the robustness of these quantum laws? They are not just rules for the vacuum. They are woven into the very essence of life, a hidden layer of physics that has been guiding living systems for billions of years, a direct bridge from the earliest moments of the universe to the flutter of a robin's wing. The same quantum principles that guide a bird's flight might also hold the secret to the birth of the cosmos. Our universe could be the ultimate quantum fluctuation, a probabilistic leap from nothing to everything. The Big Bang was not an explosion in space, but the sudden emergence of space and time themselves from a deeper, quantum realm. This is the domain of quantum cosmology, where we apply the bizarre rules of the quantum to the entire universe. Stephen Hawking, together with James Hartle, proposed a breathtakingly elegant model called the no-boundary proposal. In this vision, there is no singular, fiery beginning. If we could rewind time towards the Big Bang, the familiar arrow of time would soften and curve. At the moment of origin, time itself smoothly transitions into a fourth dimension of space, like the North Pole on a globe. You can travel north until you reach the pole, but there is no edge, no boundary, no moment of creation you can point to and say, before this, there was nothing. The universe would be entirely self-contained without a beginning or an edge, a perfect, finite whole. Hawking described this by speaking of the wave function of the universe, a single equation that encapsulates every possible history of the cosmos, with our reality being just one particularly probable path. Alexander Vilenkin offered a different but equally profound picture. He proposed that the universe appeared through quantum tunneling from literally nothing, not even empty space. Think of the quantum tunneling that lets a particle slip through an energy barrier it could not classically cross. Now, envision the entire universe as that particle, tunneling through a barrier from a state of no space, no time, and no matter, into the vibrant existence we see today. This event was then supercharged by a process known as inflationary theory. A tiny, unified patch of this new universe underwent a fantastically rapid exponential expansion, smoothing it out and setting the stage for everything to come. But the quantum origin left its mark. Inflattened fields driving this expansion were subject to the uncertainty principle, bubbling with tiny quantum fluctuations. As inflation stretched the universe, it stretched these microscopic quantum jitters into macroscopic ripples in the density of matter. These faint fingerprints of the quantum world became the gravitational seeds for all future structure. The cosmic microwave background, the faint afterglow of the Big Bang, is a snapshot of this moment. Its tiny temperature variations, mapped with exquisite precision by satellites, are the amplified imprints of those primordial quantum fluctuations. The galaxies, stars, and planets we see today are the grown-up children of quantum uncertainty. This line of thinking opens the door to an even more staggering possibility, the multiverse. If our universe can tunnel into existence from nothing, why not others? Eternal inflation suggests a vast, perhaps infinite, foam of bubble universes, each with its own unique laws of physics, a cosmic landscape of possibilities. String theory adds to this, picturing a vast landscape of possible vacuum states. With our universe just one garden in an immeasurable wilderness, can something truly come from nothing? The quantum answer seems to be a tentative yes, not as a magical event, but as a probabilistic one, governed by physical law. The question of what caused the Big Bang may dissolve, replaced by a vision of a self-actualizing cosmos, where the laws of physics are both the question and the answer. And in this cosmic story, The most extreme environments where gravity becomes all-powerful hold the next piece of the puzzle, the mysterious depths of a black hole. The serene void of space holds a perfect trap, a region where gravity is so strong that not even light can escape. Yet even these cosmic vaults are not immune to the restless churn of the quantum vacuum. Stephen Hawking made a revolutionary discovery when he applied quantum mechanics to the space just outside a black hole's event horizon. He realized that the immense gravity could tear apart the virtual particle pairs that constantly flicker into existence. In a stunning twist, one particle of the pair falls into the black hole, while its entangled partner escapes into space. To a distant observer, this stream of escaping particles looks exactly like thermal radiation, a faint heat slowly leaking from the black hole itself. This Hawking radiation carries away energy, which means the black hole must slowly lose mass, evaporating over astronomical timescales until it potentially vanishes entirely. Hawking himself described the profound consequence, stating that this process appears to destroy information. If you throw a book into a black hole, every piece of information about its atoms and words is seemingly lost when the black hole evaporates into a random, featureless spray of radiation. This creates the black hole information paradox, a direct conflict between the two pillars of modern physics. Quantum mechanics insists that information is never truly lost. The evolution of the universe must be unitary, meaning it is reversible in principle. You should always be able to run the equations backward to reconstruct the past. General relativity governing the black hole seems to allow for permanent information destruction, a fundamental violation of quantum law. Leonard Susskind and others have championed a radical solution, the holographic principle. This idea suggests that all the information describing the three-dimensional volume of a black hole is actually encoded on its two-dimensional surface, the event horizon. It is like the way a hologram stores a three-dimensional image on a flat, two-dimensional piece of film. When an object falls in, its information is not lost. It is smeared and stored on the horizon like a scrambled, universal hard drive. As the black hole evaporates via Hawking radiation, this information is slowly and chaotically released back into the universe. This leads to an even stranger puzzle, the firewall paradox. If the escaping Hawking radiation carries the information of what fell in, it must be entangled with the interior of the black hole. But it must also be entangled with the radiation that left earlier. Quantum mechanics forbids this perfect triple entanglement, a problem known as monogamy of entanglement. To resolve this, some theories suggest a dramatic solution, a wall of unimaginably high-energy particles right at the event horizon, a firewall that would incinerate anything crossing it. This directly challenges Einstein's picture of someone falling into a black hole noticing nothing special as they cross the horizon. String theory offers a different picture, where black holes are not simple pits but fuzzballs, complex structures of strings whose details prevent a sharp horizon from forming. The core question remains unresolved. Is information truly lost, or is our understanding of spacetime profoundly incomplete? How can a theory of quantum gravity preserve information without violating other cherished principles? The fate of information in a black hole is not just about stars and singularities. It is a fundamental test, probing whether the universe is ultimately predictable and lawful, even in its most extreme environments. Our two most powerful theories of reality speak different languages. Quantum mechanics paints a universe of chance and particles, while general relativity describes a cosmos of curved spacetime and gravity. For decades, these two pillars have stood in magnificent, stubborn isolation. Uniting them into a single framework, a theory of quantum gravity, is the final great frontier of physics. The challenge is that gravity resists being quantized. In other forces like electromagnetism, We picture force carrying particles, virtual photons, being exchanged. But when we try to apply the same math to gravity, imagining a graviton particle, the equations explode into infinities that cannot be tamed, a problem known as non-renormalizability. This mathematical breakdown hints that our concepts of space and time are not fundamental, but merely emergent approximations. The scale where this happens is almost unimaginably tiny, the Planck length. This is a distance so small that if you enlarged an atom to the size of the known universe, the Planck length would be roughly the height of a single tree. At this scale, spacetime itself may cease to be smooth and continuous. It might become granular, a foam of discrete, quantized units. Physicist Carlo Rovelli, a founder of loop quantum gravity, describes space not as a backdrop, but as a network of woven loops, a spin network. In this picture, space is not infinitely divisible. It is made of tiny, finite grains, much like a piece of fabric is made of individual threads. The area and volume of space are quantized, coming in specific, discrete amounts. Another leading approach is string theory. Here, the fundamental objects are not point particles but incredibly tiny, vibrating strings. Edward Witten, a leading string theorist, has spoken of its mathematical elegance, suggesting it is a piece of 21st century physics that fell into the 20th century by chance. The different vibrational patterns of these strings correspond to different particles. A graviton emerges naturally from this framework, a closed string vibrating in a specific way. String theory requires extra dimensions of space, curled up into shapes so small we never perceive them. It also gives rise to the holographic principle, the radical idea that the information within a volume of space can be fully encoded on its boundary, just as the information for a three-dimensional hologram is stored on a two-dimensional surface. This principle finds its concrete realization in the work of Jacob Bekenstein and Stephen Hawking on black hole entropy. They showed that the entropy of a black hole, a measure of its information content, is proportional to the area of its event horizon, not its volume. This was the first strong hint that our three-dimensional reality might be a projection from a two-dimensional surface. A third, more recent contender is asymptotically safe gravity. This approach suggests that gravity might be renormalizable after all, if we treat it correctly at very high energies. The strength of the gravitational interaction could reach a fixed point, a safe harbor, preventing the mathematical infinities. What do these competing visions tell us? They suggest that the nature of time might be an illusion, a concept that emerges only in the large-scale world. They imply that the Big Bang might not have been a singular beginning, but a bounce from a previous universe. Is the fabric of spacetime a smooth, continuous sheet, or is it a digital pixelation, a tapestry woven from individual threads? The pursuit of quantum gravity is not just about finding new equations. It is about answering the most profound questions of existence. What is time? What is space? And what truly happened at the very dawn of creation? The answer waits at the Planck scale, where the quantum nature of gravity reigns supreme. But what does this quantum strangeness actually mean? Beneath the perfect accuracy of the equations lies a deep philosophical chasm, a question with no single answer. We step into an arena where physicists and philosophers debate the very nature of reality itself, each offering a different interpretation of what the math describes. The oldest and most famous is the Copenhagen interpretation, championed by Niels Bohr. In this view, particles do not have definite properties until they are measured. The wave function is not a real thing, but a mathematical tool that encapsulates our knowledge, collapsing from a spread-out probability into a single fact the moment an observation is made. Bohr himself argued that it is wrong to think the task of physics is to find out how nature is. Physics concerns what we can say about nature. This framework draws a sharp line between the quantum world of potential and the classical world of definite apparatus and observers. It is a pragmatic approach that has guided generations of physicists, yet it leaves the act of measurement mysteriously undefined. In stark opposition stands the many worlds interpretation, proposed by a young Hugh Everett. He took the mathematics at face value, suggesting that wave function collapse is an illusion. There is no collapse. Instead, at every quantum decision, the entire universe splits. Every possible outcome actually happens, each in its own newly branched reality. In one world, the electron goes through the left slit. In another, it goes through the right. You yourself split into multiple versions, each unaware of the others. As Everett described it with his relative state formulation, all elements of a superposition are equally real. This interpretation is breathtaking in its scope, eliminating the need for a special measurement rule but at the cost of an infinite, ever-branching multiverse. Then there is the de Broglie-Bohm pilot wave theory, a vision of a deterministic quantum world. Here, particles are real and have definite positions at all times, guided by a hidden pilot wave. Think of a surfer riding a wave. The surfer has a specific location, but their path is dictated by the shape and force of the wave beneath them. In the double-slit experiment, the electron particle actually goes through only one slit, but the pilot wave travels through both, creating an interference pattern that guides the particle to the correct spot on the screen. This theory recovers all the predictions of standard quantum mechanics, but paints a picture of a universe that is both real and deterministic, though deeply non-local, with influences connecting everything instantaneously. Other views seek a middle ground. Objective collapse models propose that wave functions collapse spontaneously when a system reaches a certain size or complexity, a physical process unrelated to consciousness. Quantum Bayesianism, or Cubism, takes a radically subjective stance, treating the wave function as a personal betting tool, a representation of an agent's beliefs and expectations about the world. So, how do we see the double-slit experiment through these different lenses? For Copenhagen, the electron has no path until measured. For many worlds, it goes through both slits, and the universe splits to accommodate each possibility. For pilot wave, it has a definite path guided by an invisible wave. Which interpretation feels most intuitive to you? Does the choice between them actually change the physics? For most experimental outcomes, no. They all make the same predictions, which is why the debate continues. Yet the choice profoundly influences how we think about quantum foundations, reality, and our place within it. This is not just academic. The interpretation we favor shapes the questions we ask next, guiding our search for a deeper theory that might one day tell us what is truly real. Beneath the equations and experimental results lies a deeper quest, a search for the soul of quantum theory. This is the field of quantum foundations, where we question the very assumptions the theory is built upon. It asks not just how the quantum world behaves, but what its strange rules are telling us about the nature of reality. The puzzles we have encountered, from entanglement to wave function collapse, are not mere curiosities. They are signposts pointing toward a more complete picture of the cosmos. John Bell, the physicist who found a way to test Einstein's spooky action, cut to the heart of the matter. He argued that the universe must be fundamentally non-local, that influences can connect distant events without traveling through the space in between. His theorem ruled out local hidden variables, those secret instructions that would have restored a classical, common-sense reality. But the strangeness does not stop there. Another profound limit is contextuality, a concept crystallized in the Cauchy-Specker theorem by Simon Cauchy and Ernst Specker. Contextuality reveals that the properties of a quantum system are not inherent, fixed values waiting to be discovered. Instead, what you find depends on how you choose to look. An electron does not possess a definite spin in a specific direction independently. If you measure its spin along the vertical axis, you might get a clear answer. But if you then decide to measure it along a diagonal axis, the result is not predetermined. The value you get depends on the full context of the measurement, the complete set of questions you ask simultaneously. This shatters the classical idea that objects have a suite of independent properties. These discoveries are formalized as no-go theorems, powerful mathematical proofs that certain intuitive ideas about reality are simply incompatible with the experimental facts. They build fences around what is possible, forcing us to abandon cherished assumptions. One of the most elegant demonstrations of this is the gigahertz experiment, named for Daniel Greenberger, Michael Horn, and Anton Zeilinger. It is a game played with three entangled particles. Unlike Bell's test, which relied on statistical inequalities, the gigahertz setup provides a direct, all-or-nothing contradiction between quantum predictions and any local hidden variable theory. The result is so clear that a single run of the experiment can, in principle, reveal the conflict. A stark demonstration of non-locality without the need for statistics. This forces a fundamental question. Are quantum states real? Is the wave function a direct description of physical reality? Or is it merely epistemic, representing only our knowledge or ignorance about a system? The PBR theorem, developed by Matthew Pusey, Jonathan Barrett, and Terry Rudolph, provides a strong argument against the epistemic view. It suggests that if the world behaves according to quantum mechanics, then the wave function must be a real, physical state, not just a representation of our incomplete information. This pushes us toward a view where the blur of superposition is an objective feature of the world. Some researchers even explore quantum logic, an alternative form of reasoning where the distributive law of classical logic, the rule that links and/or, breaks down. It is a formal system built to reflect the actual behavior of quantum systems, a mathematics where a particle can be here or there. But the concept of here and there does not follow the familiar rules of common sense. Why does this abstract, foundational work matter? It is not merely philosophy. By probing the deepest principles of quantum theory, we are laying the groundwork for the next revolution. Understanding non-locality and contextuality is already guiding the design of new quantum algorithms and more robust forms of quantum cryptography. The quest to understand what is real is directly fueling the technology that will shape our future. If the properties of the world are not fixed but depend on the questions we ask, what does that say about our role as participants in the cosmos? These abstract debates are already giving birth to a technological revolution. Quantum theory is stepping out of the laboratory and into our world, powering devices that promise to transform everything from medicine to navigation. This shift from pure theory to tangible transformation hinges on our ability to harness quantum effects like superposition and entanglement for practical use. Quantum sensors are among the first of these devices to make a profound impact. They exploit the exquisite sensitivity of quantum states to the slightest environmental change. An atomic clock, for instance, is not a classical timepiece. It works by using microwaves to probe the precise quantum transition between two energy levels in an atom, typically cesium or rubidium. The unwavering regularity of this atomic vibration defines the second itself. This quantum precision is the silent engine behind the global positioning system. Every GPS satellite carries an atomic clock, and the breathtaking accuracy of your location on Earth, often to within a few meters, depends entirely on the flawless ticking of these quantum devices. Without them, the entire system would drift into uselessness within hours. Physicist Mikhail Lukin has spoken of a coming age of quantum advantage, where we use quantum systems to do things that are practically impossible with classical technology. This advantage is not just about raw power, but about a new kind of perception. Quantum imaging allows us to see the world in unprecedented ways. Magnetic resonance imaging, or MRI, is a widespread quantum technology. It relies on the quantum property of spin in atomic nuclei, typically hydrogen within the water molecules of our bodies. By placing a patient in a powerful magnetic field and pinging these nuclei with radio waves, we can read their quantum responses to construct detailed, non-invasive images of our internal organs. Newer techniques, like ghost imaging, use entangled photons to create images of objects with light that never actually illuminates them, a capability with potential for low-light medical scans or secure surveillance. The broader field of quantum metrology uses entanglement to smash what was once thought to be the ultimate limit of measurement precision, the standard quantum limit. By entangling a group of particles, we can measure physical quantities like magnetic fields, gravitational waves, or rotations with a sensitivity that no classical sensor could ever achieve. Imagine a future where such sensors can map the tiny magnetic fields of a human brain from outside the skull, diagnosing neurological conditions long before other symptoms appear. Even the simple need for true randomness is fulfilled by quantum mechanics. Classical computers can only generate pseudo-random numbers, following complex but ultimately predictable algorithms. A quantum random number generator, however, harvests genuine randomness from fundamental processes like the unpredictable decay of a radioactive atom or the random path a photon takes through a beam splitter. This perfect unpredictability is the bedrock of modern cryptography and secure communication. Perhaps the most powerful near-term quantum tools are quantum simulators. These are specialized quantum systems, often built with arrays of ultra-cold atoms or ions, designed to mimic and model other quantum systems that are too complex for any supercomputer to handle. They act as analog computers for nature's most intricate puzzles. We can use them to unravel the secrets of high-temperature superconductivity, design new molecules for life-saving drugs atom by atom, or solve optimization problems in logistics that would take centuries to calculate by other means. How will these technologies reshape our daily lives? We might have hospitals that can peer inside a single living cell, navigation systems that never fail, and a global internet secured by the laws of physics themselves. Yet such power also brings profound ethical questions. Who will have access to these technologies? Could quantum sensors lead to unprecedented levels of surveillance? How do we prevent a new quantum divide between those who control this technology and those who do not? The path forward is not without its immense challenges. Scaling these delicate quantum systems from controlled lab experiments to robust, mass-produced devices is a monumental task, but the transformation has already begun, quietly ticking in the satellites overhead and humming in the hospital down the street, a testament to the strange and powerful laws that govern our reality. Building a machine that thinks in quantum superpositions is like trying to sculpt with smoke. The very properties that give it power are the ones that fight hardest against being contained. To harness this potential, we must create an artificial environment of almost impossible perfection, a world within a world where the normal rules of heat and noise do not apply. The heart of this struggle is the qubit, a flickering candle of information that any passing breeze can extinguish. These breezes are not just air, but any tiny vibration, any stray electromagnetic wave, or even the faint warmth of the materials holding the qubit itself. This is the central technical hurdle, the fight against decoherence, and it dictates that most quantum processors must live in elaborate cryogenic systems, chilled to a whisper above absolute zero. Inside a dilution refrigerator, temperatures plunge to within a few thousandths of a degree of that ultimate cold. The processor at the very center is colder than the vacuum of deep space, a necessary condition to freeze out the thermal noise that would otherwise shatter its delicate quantum states. But even this extreme isolation is not enough. The materials used to fabricate the qubits themselves must be engineered with atomic precision, as even a single magnetic impurity or a loose atom can act as a source of decoherence, constantly whispering to the qubits and breaking their concentration. Physicist John Preskill gave a name to our current stage of development, calling it the noisy intermediate-scale quantum era, or the NISQ era. In this time, we have quantum processors with dozens or even hundreds of qubits, but they are noisy. Their quantum states are fragile and short-lived, and the operations we perform on them, known as quantum gates, are imperfect. The key metric here is gate fidelity, a measure of how accurately a quantum operation is performed. If a gate has a fidelity of 99.9%, that sounds incredibly high. But for a complex calculation requiring millions of gates, that tiny 0.1% error rate compounds catastrophically, dooming the computation to failure. This is why scaling up is not a simple matter of adding more qubits. Adding qubits increases the control complexity exponentially. Each new qubit needs its own control lines, its own readout circuitry, and it must be able to interact precisely with its neighbors, all without introducing more noise into the system. It is a wiring and control nightmare, a ballet of microwave pulses and magnetic fields performed on a chip smaller than a fingernail. So how do we move beyond the NISQ era? The path forward lies in quantum error correction. This is a brilliant conceptual leap where we stop relying on a single, fragile physical qubit, and instead use many of them to create one robust logical qubit. The information of that single logical qubit is spread out across a whole array of physical qubits, like writing a message with a pen that has many tips. By constantly measuring the relationships between these physical qubits in a clever way, we can detect the telltale signs of decoherence and correct errors without ever directly looking at, and thus collapsing, the core information. This process builds a fortress around the quantum state, but the cost is immense. Current estimates suggest that a single, stable logical qubit capable of running a useful algorithm might require thousands or even millions of these error-prone physical qubits working in concert. We are not just building a new computer. We are building an entire ecosystem designed to protect a thought from the universe itself. How close are we to this fault-tolerant future? The gap is still vast, but it is closing. The breakthroughs we need are not just in physics, but in materials science, in control electronics, and in software. It requires a new generation of engineers and scientists who understand this strange new world. The ultimate success of this quantum endeavor hinges on our ability to educate, to build the minds that will one day build the machines. The equations of quantum mechanics are no longer confined to postgraduate textbooks. A quiet revolution is unfolding in classrooms and online platforms, preparing a new generation to speak the language of the quantum world. This shift in education is not just about learning formulas. It is about cultivating a quantum intuition, a mindset comfortable with probability clouds and entangled states from a surprisingly young age. Educators are discovering that the conceptual hurdles of quantum theory, like superposition, can be overcome with the right tools. They use tangible analogies, like a spinning coin that is neither fully heads nor tails, to give students a mental hook for these abstract ideas. The goal is to move beyond rote memorization and foster a genuine feel for this strange new reality. Initiatives like quantum summer camps and online courses from organizations like Qiskit are breaking down barriers, making the subject accessible to anyone with curiosity and an internet connection. These programs emphasize an interdisciplinary approach, blending physics with computer science, philosophy, and even art. As one leading quantum educator notes, the next breakthrough will not come from a physicist working alone, but from a team that includes a programmer, an engineer, and a creative thinker who learned quantum principles in high school. Hands-on experimentation is crucial to this learning. Students are not just reading about qubits. They are building simple quantum circuits in virtual labs. The IBM Quantum Experience, for instance, allows users from around the world to run algorithms on real quantum hardware through the cloud. This direct interaction transforms the subject from a theoretical puzzle into a living, breathing technology. Educational games are another powerful tool, turning complex concepts like quantum teleportation into engaging puzzles that build understanding through play. How can we improve quantum literacy for everyone? It begins by demystifying the field, presenting it not as an impenetrable mystery, but as a new set of rules waiting to be mastered. What role does raw curiosity play? It is the essential fuel. The students who today are visually programming a quantum computer to play a game are the same minds who will tomorrow design the unbreakable encryption and life-saving drugs of our future. Their education is the bridge from our current quantum questions to the profound answers yet to come. The same foundational curiosity that guides our classrooms today is already charting a course for tomorrow's discoveries. Our journey into the quantum realm is far from over. It is accelerating toward a horizon filled with possibilities that will reshape our understanding of the cosmos. In the coming decades, quantum research promises to unlock secrets hidden in the fabric of spacetime itself. We stand at the threshold of a new frontier, where the very tools born from quantum theory will allow us to probe its deepest implications. One of the most profound goals is the direct detection of quantum gravity. For decades, this force has resisted integration into the quantum framework. But future experiments using exquisitely sensitive quantum sensors might finally hear its faint whisper. Imagine a network of devices that can measure the subtle ripples in spacetime caused by the quantum jitter of particles themselves. These vibrations, occurring at the Planck scale, could provide the first experimental evidence that spacetime is not smooth, but granular. Such a discovery would bridge the last great divide in physics, uniting the very large with the very small under a single set of laws. Closer to home, the quest for room temperature superconductors is reaching a fever pitch. These are materials that can conduct electricity with perfect efficiency, without any loss to heat, and without requiring costly supercooling. Using powerful quantum simulators, we can now model the bizarre behavior of electrons in exotic materials atom by atom. This could lead us to design a superconductor that works in everyday conditions, revolutionizing our energy grid, making levitating trains commonplace, and enabling a new generation of ultra-efficient electronic devices. The physicist Michio Kaku has often spoken of such materials as the key to a Type 1 civilization, one that masters all the energy of its planet. This computational power will also transform artificial intelligence. Quantum artificial intelligence could analyze complex datasets in ways that are impossible for classical machines. It could discover new drugs by simulating the quantum chemistry of millions of candidate molecules simultaneously, or optimize global supply chains by instantly calculating the most efficient routes among countless variables. The futurist Ray Kurzweil has speculated that the merging of quantum computing with AI could lead to an intelligence explosion, allowing us to solve grand challenges like climate change or disease in a fraction of the time. To build these powerful quantum computers, we are exploring radical new architectures. Topological quantum computing is one of the most promising paths. Instead of relying on the fragile state of a single particle, this approach stores information in the global properties of a system, in the braiding of quantum world lines. Think of it as storing a number not on a single, easily scratched coin, but in the complex knot of a necklace. Tug on one part, and the knot remains the same. This inherent stability could create qubits that are naturally protected from decoherence, paving the way for robust, fault-tolerant quantum machines. Our quantum reach may even extend to the stars. Interstellar quantum communication envisions a network of satellites using entangled photons to create a secure channel across the solar system. This would not be for faster-than-light messaging, but for establishing a cosmic internet with unparalleled security, allowing future colonies on Mars or beyond to communicate with Earth without fear of interception. And through quantum cosmology, we can test theories of the universe's origin. By comparing the quantum fluctuations imprinted on the cosmic microwave background with predictions from various models, we can refine our understanding of the Big Bang and the potential existence of a multiverse. Perhaps one of the most haunting quests is the search for dark matter. This invisible substance makes up most of the mass in the universe, yet it has eluded every classical detector. The next generation of quantum sensors could change that. These devices, using supercooled crystals or clouds of entangled atoms, are so sensitive they could feel the gentle bump of a dark matter particle as it drifts through the Earth. Detecting this ghostly matter would solve one of the greatest mysteries in modern cosmology and reveal a hidden component of reality. What cosmic secrets will quantum mechanics unveil next? Will it show us that our universe is just one thread in an infinite quantum tapestry? The future of this exploration hinges on our relentless curiosity, on our willingness to keep asking questions that challenge the very nature of reality. Each answer we find does not close a door, but opens a gateway to a dozen new and even more wondrous mysteries. Quantum mechanics does more than describe atoms. It stirs something deep within the human spirit, a resonance with the mysterious that feels almost primal. These are not just abstract rules for tiny particles. They are profound metaphors that have seeped into our art, our stories, and our deepest questions about who we are. The unsettling idea of a world built on probability, where certainty is an illusion, mirrors the very unpredictability of our own lives. We find our own fragile existence reflected in the shimmering potential of a quantum state. The writer Alan Lightman captured this perfectly, suggesting that the most profound discoveries in physics force us to reconsider our own place in the grand scheme, to wonder if our sense of a solid self is as much an illusion as a particle's definite position. This is why quantum concepts captivate artists and filmmakers. The movie Interstellar did not just use wormholes and time dilation as plot devices. It used them to explore human connection across distorted spacetime, making the cosmic intimately personal. The film's emotional core, the bond between a father and a daughter stretched across relativistic years, is a direct confrontation with the quantum-informed idea that time is not a universal constant, but a personal experience. Literature is filled with these explorations. Stories that play with multiple timelines or parallel lives draw directly from the many worlds interpretation, allowing us to ponder the roads not taken in our own lives. The indeterminism of the quantum world liberates us from a clockwork universe, opening a space for free will, for chance, for the beautiful accidents that define our histories. There is a striking, and often discussed, parallel between these ideas and ancient Eastern philosophies. The Hindu concept of Maya, the world as illusion, finds a curious echo in a universe where particles have no definite reality until measured. The Buddhist teaching of dependent origination, where nothing exists independently but only in relation to everything else, resonates powerfully with the entangled nature of quantum systems. The physicist Fritjof Capra explored this in his book The Tao of Physics, noting that modern physics and Eastern mysticism, though arising from completely different methods, seem to converge on a similar view of the world as an interconnected, dynamic whole. Why does this matter to us, sitting far removed from the lab? Because these scientific discoveries provide a new vocabulary for age-old human anxieties and wonders. They give form to our intuition that the world is stranger and more wondrous than it appears. The drive to understand quantum mechanics is the same drive that leads us to gaze at the stars or create great works of art. It is the human need to find meaning, to push against the boundaries of the known. How does knowing a particle can be in two places at once change your perspective on the choices you face? Does the spooky connection of entanglement make the bonds we feel with distant loved ones seem any less magical, or any more profound? We are drawn to these quantum mysteries because they are, ultimately, mysteries about ourselves. They challenge our most basic assumptions about identity, connection, and reality, inviting us to see the universe not as a cold machine, but as a participatory, unfinished symphony. This reflection on our place in a quantum world brings us to the final step in our journey, a look at where these revelations are leading us and what they mean for the future of humanity itself. Our journey across the atomic horizon reveals a universe where certainty is an illusion and connection is instantaneous. We have watched the solid ground of classical physics dissolve into a shimmering cloud of probabilities, where particles exist in multiple states at once and communicate across vast distances with spooky intimacy. This is not a flawed description of reality, but a deeper one, challenging everything we thought we knew about the world. The key takeaway is not just a list of bizarre effects, but a fundamental shift in perspective. We have moved from a universe of clockwork predictability to one of dynamic potential, from isolated objects to an entangled whole. This new vision powers the technologies that will define our future, from unbreakable encryption to computers that can solve problems we can barely even frame today. The physicist Niels Bohr offered a piece of profound wisdom that captures the heart of this quantum world. He said that the opposite of a correct statement is a false statement, but the opposite of a profound truth may well be another profound truth. This is the essence of quantum mechanics. Light is both a particle and a wave. An electron has no position until you measure it. A cat can be both alive and dead. These are not contradictions to be resolved, but complementary truths to be embraced. This framework teaches us a powerful lesson in humility and wonder. It shows that our intuition, built in a world of medium-sized objects, is a limited guide to the underlying nature of reality. The universe is far stranger, more interconnected, and more mysterious than we ever imagined. So as you reflect on these ideas, let them settle. How does a universe of probability and participation change your view of your own existence, your choices, and your connection to everything else? The quantum frontier does not end with this exploration. It begins with your curiosity. We would love to hear your thoughts in the comments below. And if you are eager for more journeys to the edge of understanding, subscribe for our next deep dive into the mysteries